My name is Ian McLaughlin, and I'm a PhD in Neuroscience from the University of Pennsylvania. And I hope you had a lovely 4th of July, or at least those of you who celebrate that kind of holiday on that day. So I've talked about COVID-19 for the past several weeks, and I thought it might be about time we take a bit of a break and talk about some of the topics in neuroscience that drew me into the subject in the first place. So, one of the sort of classic metaphors or like heuristics that we use to understand how the brain works is by comparing it to a computer, and it totally makes sense. You know, particularly these days, computers are capable of things that would have sounded like complete fantasies, like even when I was a kid. And to be fair, computers are superior to humans in some specific categories. More on that later. So an article was published in Nautilus, the online outlet, by Liqun Luo, who's a neuroscientist at Stanford, and it seems like it's a bit of a sample of a textbook that he's about to put out on introductory neuroscience. But anyways, this short article engages this comparison, brains versus computers, and I think he does a good job of honing in on one of the specific features of the brain that explains a lot about why, despite how superior computers have become at specific things, again, like, calculations and extremely precise memory, humans remain superior at more complicated outputs, like catching a ball that was thrown at you, even if it was a complete surprise. So I'll put a link to the article in the description below, and it's not very long. He does a good job of writing it in a way that it'd be coherent to people outside of the discipline. And before we get too far into the topic, I want to emphasize that this is just one of the meaningful differences between computers and human brains that explains how different our capabilities still are. But, okay, with that said, let's get into this particular argument. So Dr. Luo does a good job of concisely articulating some of the most basic comparisons that one might make to understand the differences between a computer and the brain. So, for example, he brings up comparisons like, the most basic units of what enables a computer to compute versus neurons and synapses in the brain, and ultimately makes an argument about one of the most significant distinctions that I think is worth discussing. So, to get started, here's a table that he provides in the article. And in it you can see that he breaks down, the comparisons into categories like numbers of basic units, again, like neurons and synapses in the brain versus transistors in a computer, to the speed of basic operation, precision, power consumption, and things like that. So one of the most meaningful differences arises from just a few of the sort of property comparisons, and I think it's worth focusing on two in particular. So first, the speed at which signals are transmitted between the most basic units of a computer and the brain. So in the brain, signals in which we're interested right now are called action potentials or impulses. That might be a word that you've used in the past or heard in the past. And those signals travel between neurons. One neuron fires an action potential or an impulse, and it propagates down like a cable towards a bunch of other neurons. And so here's an image you would see if you were in an intro neuroscience course, to give you sort of an idea of what action potential propagation looks like. So, but to sort of start, and so you can see the one neuronal cell body or soma sending a signal down its axon to the projections that will then be received by another neuron. And so to give you a sense of the complexity that we're talking about here, here's a neuron that's almost certainly been extracted and basically just sort of sitting in a petri dish. And so you can see that little blue spot in the middle there, that's the body of the neuron. Once again, we call it the soma. And you can see that once it fires its action potential or impulse, that signal travels down all of those little projections emerging from that body, from that central body, in all directions. And so ultimately those signals will be received by a ton of other neurons, which may or may not then, subsequently fire their own action potentials. And so, once you scale it up to an entire brain, you can start to get a sense of just how frequently this is happening among the sort of 80 billion, 86 billion or so neurons in the brain. So here, it's kind of a cool little animation. And it's happening constantly. Even if you're just sitting and staring at a wall, when you're sleeping or just zoning out and daydreaming. And so, you can also, just from these, you can sort of get a sense of the time scale with that animation in the middle there. So by the time scale, I mean, you can get a sense of how quickly signals are traveling between neurons, and that's one of the most meaningful differences between computers and brains. So the highest frequency of a neuron firing an action potential, which one, once again, it's basically what you probably call an impulse, is about 1,000 times per second. Right? So in other words, the fastest transmission between neurons is on the order of 1 millisecond. and it varies between different neurons and different connections. So if just to give you an example, right? So if one neuron next to another neuron is firing an impulse, it takes less time for the signal to travel down those cables that connect the neurons, axons, than it'd take for a neuron to communicate with another one that's like on the other side of the brain, right, super far away. But that's essentially the brain's like speed of light, right? We can't go much faster than that. And don't get me wrong, that probably sounds incredibly fast, and it is super fast. It's like incomprehensibly fast, actually. It's so fast in neuroscience that we sometimes use sound to help us to get a sense of just how fast a neuron is firing. And to give you a sense of what this sounds like, I'm going to try this out for a second, and I hope it works. It's the first time I try this. But before I start it, you should hear like a bunch of clicks, basically, like super fast clicks, like brr, brr, like something like that. Maybe sort of what you might imagine like electricity would like sound like. And I should, so, and this is also like the first time I've ever done this, so, if you're wearing headphones, maybe like be ready to rapidly eject them from your ears, or just forgive me if you can't hear it. Okay, here we go. Okay. So the sound you just heard were the sounds of neurons firing action potentials. And I'm pretty sure that these were somatosensory neurons, and somebody was just recording what happened when an animal was sort of being like tickled along a specific part of the body. It's either that or they're recording from neurons that control head direction. So like specific neurons firing when an animal points its head in one direction or the other, right? Neurons literally control that. Yeah, right. And by the way, this sound, this is basically the first sound or like real kind of sensory experience of neuroscience I ever had. I went into a lab of a college professor of mine named Newton Kopp, Dr. Newton Kopp, an absolutely perfect scientist name, and he was working with some other college student, working on another college student, recording, from some neurons or another, and I just heard these super weird click sounds. It was just like kind of surreal. And he actually never even explained it on that day. He's a fantastic professor, but he was just like, we were just talking as though it like wasn't happening. It was kind of weird. But so for the purposes of this conversation, it doesn't really matter where in the brain these neurons are. All you're hearing in those clicks is just like a neuron firing an impulse. So it's super fast, right? But as fast as that may seem, each and every one of your 86 billion neurons transmitting signals to one another at that speed, it's not even close to the speed at which the basic units of computers operate. So Dr. Luo notes that the sort of standard personal computer today, like whatever you're perhaps using, can perform mathematical operations like addition at the speed of 10 billion per second, right? 10 billion per second. And that's compared to like our 1,000 per second. And so, he suggests that this works out to the brain operating at about 10 million times more slowly than a computer. So, he says, quote, your brain is 10 million times slower than a computer, right? So this is like one of those comparisons that's almost like so general that it's almost meaningless, but only almost. I mean, for sure his point is correct. Like the basic units of computers, transistors, can handle signaling at far higher speeds than neurons do. And that's really the point he's conveying. So, okay, so that's speed. He also highlights the level of precision that computers can manage compared to the human brain. So computers can work with numbers that at like an incredibly high level of precision. So many of us can do simple division in our head, right? Like 25 divided by 5, super simple. And some folks can work with, like what they can imagine what 1 divided by 3 looks like. Just a bunch of 3s after a decimal point. All right, no biggie, right? But when the result of like division or an exponent or a square root or whatever it is results in like a gigantic number of units, it becomes pretty impossible for the human brain to really grasp what those numbers really mean with any precision. Like, think of a number followed by a decimal point followed by like 500 units. We'd obviously just like round that number up to the most intelligible number to work with. Well, computers don't have to do that, right? They can operate with those numbers, with numbers that have an absurd number of digits, which means that they're working with numbers that are far closer to the actual number that's meaningful than we can. So, in other words, they can operate at a far higher level of precision than we can. And I probably don't have to convince you that computers, despite that, are still unable to perform a bunch of tasks that humans can. Not only that we can, but that we can do these things without really exerting incredible effort. Yeah, right. Oh, and not only that, but our brains can execute these tasks using far less energy than computers. And Dr. Luo describes this difference in energy consumption as being tenfold lower in the brain than it is with a standard personal computer. And, frankly, I've seen a bunch of different manifestations of this comparison, like energy use between the brain versus a computer. But they all emphasize that the brain is significantly more energy efficient than computers. Keep in mind, the brain does use about 20% of the caloric energy that's provided by the body. And it's just like sitting there bathed in salt water, not moving or really doing much of anything physical, at least not obviously. They're just producing signals among, it's 86 billion neurons and approximately as many of their, partner cells glia. It's an incredibly expensive organ to have. Not all parts of the brain consume energy at the same rates, by the way, right? Like auditory processing or ability to hear things almost certainly consumes quite a bit more energy than olfaction or your ability to smell. But regardless, the point is that the brain operates at a pretty high energy efficiency relative to computers. And, of course, it doesn't need to be plugged into a wall to work. You can, eat a steak, a cheeseburger, a lobster, or, kale salad, and the brain will just take what it needs to do its work. And, of course, that's, not considering what, optimal nutrient proportions might be. But, try running your computer off of, ramen noodles like my brain did when I was in college. And tell me, how does it work, right? So the brain has some pretty impressive energy versatility. But what can it do better than computers, and why? So, we've seen all those videos. Oh, darn, I don't think I queued that up. Let's see if I have it. Oh, yeah, here we go. Yeah, so we've seen these videos from Boston Dynamics of, engineers kicking robot dogs who are, able to recover incredibly well. And I just saw this video that's supposedly from them as well, from Boston Dynamics, which looks super creepy and sort of humanish, right? Uncanny Valley-ish. And so, computers can handle locomotion, walking and so on. And, even super challenging issues like, involving locomotion, like recovering from a blow to the side, a surprise blow. But computers still can't quite compete on a tennis court with a human, and certainly not restricted to the size and mass of a human, right? So as Dr. Luo puts it, quote, "For example, a professional tennis player can follow the trajectory of a tennis ball after it is served at a speed as high as 160 miles per hour, move to the optimal spot on the court, position his or her arm, and swing the racket to return the ball in the opponent's court, all within a few hundred milliseconds." So, computer systems aren't close to that level of computational and physical performance. So, what's the secret sauce in the human brain? Well, as Dr. Luo highlights, what I think is one of the central ingredients, computers perform tasks largely in serial steps, right? They obey a largely sequential flow of instructions. And the sequential flow of these instructions can be super complicated, but it's ultimately sequential. And, at each step, high precision is necessary. Otherwise, errors can become amplified as it, progresses through those steps. And, it's absolutely worth noting that there are, many examples of serial signaling within the brain and nervous system as well, like hitting a pitched baseball, right? The photons are bouncing off the ball. They need to splash up against the photoreceptors in the retina, which then need to send their signals to the visual cortex, which then need to be, decoded for color, shape, direction, speed, and all those things. And then signals emerge from the brain out through the spinal cord, towards voluntary muscles to move the arms, torso, and legs to smack the baseball. So what's the important ingredient there? What's the difference? So as Dr. Luo puts it, massively parallel processing. So by that, what he means is that our brains evolved to exploit just how many neurons we have, as well as how many connections each neuron tends to have. And so, in other words, many components of a challenge, like hitting a baseball, are processed simultaneously or nearly simultaneously, rather than one step waiting for the other to be completed. And not only that, but when it comes to something like hitting a baseball, there's a ton of memories available to somebody who's trained to be excellent at hitting baseballs, like knowledge of knowledge of what a particular pitcher's strategies are, sensitivity to specific body language of a pitcher, like knowledge of what the most likely pitch might be given who's on base, and so on, right? all of that feeds into what the spinal cord ultimately receives to deliver movement commands to the arms, torso, and legs to swing a bat. And there are some specific anatomical features of the human brain that may explain why it is that humans are capable of all the things that we can do that other members of the animal kingdom can't. But that's like a topic probably for another day. But the point here is that since neurons collect and send inputs and outputs to somewhere around 1,000 connections, and that's a general sort of average, the degree of connectivity between each individual neuron enables extremely rapid and efficient communication. And so, to be clear, like that number of connections each neuron will have will vary very widely, depending on where in the brain the neuron is and what kind of neuron we're discussing. But the fundamental principle is what matters. It's the vast connectivity within the brain that enables this massively parallel processing, and that's what's keeping us from being totally dominated by computers, at least for the time being. Okay, so and who knows, what'll be possible when computers are more intimately integrated into the human nervous system. All right, that's what I had for you today. Massively parallel processing, important feature of the human brain. So why don't we just go ahead and start the live half? We do this. We do this. Hello, everybody. My name is Ian McLaughlin. I am a PhD in neuroscience from the University of Pennsylvania. And on YouTube, I just talked about what it is about the human brain that's distinct from computers that has prevented computers from dominating us in sort of intelligence. So you can check that out by searching like anthropoid brain Ian or something like that, and you'll be able to find it. It was based off of an article, probably do that. An article written by a neuroscientist from Stanford, I believe, Dr. Luo, and it's pretty good. It also the article is in Nautilus, and he does a good job of like writing it so that it's intelligible to people who aren't neuroscientists. Hello, Joy. Good to see you. So you can check that out. I hope everybody had a pleasant 4th of July, if you celebrate 4th of July. And I can tell you that my past week has been fairly miserable because I've been continuing to revise this paper of mine. Do you think AI will ever actually be conscious or just emulating? Yeah, so that is like a sort of classic debate within neurophilosophy or philosophy of mind. And oftentimes those debates kind of boil down to semantics. Like, okay, what are you defining by conscious? Like, if you just define conscious as, sort of like the Turing test style, where if you can't distinguish this thing from having consciousness, then that's consciousness. Others, however, and these tend to be people who within the discipline who aren't involved in like actual scientific research, but contribute very important philosophical explanations. They argue that there is some feature of the wet work of the human brain that enables us to experience what it's like to have an experience, right? What it's like to see the color red, or what it's like to be a bat. That was sort of a famous essay written by a neurophilosopher named Jeffrey Nagel, I think. His last name was definitely Nagel. I can't remember if it was Jeffrey. My perspective is, that it may be different. It may not be identical to human consciousness, but it will be a form of consciousness. And there's sort of like a chauvinism, right, to saying that like, oh, well, you'll never have human consciousness. Well, it's like, that's not even necessarily superior to have. Yeah. And so I talked a little bit about sort of like the nuts and bolts of one of the set of nuts and bolts that distinguish a human brain from a computer, in sort of like how information is processed that has enabled human brains to stay like a step ahead on YouTube. Hi again. Hope you have a good one. I did. Thank you. Does neuroplasticity work in those with autism to improve their symptoms? So yes. So neuroplasticity, it is an ongoing process over which we have no control. It's just happening. You can't stop it. And the goal is, one goal is to do your best to ensure that neuroplasticity is influencing brain adaptation in a way that you would want. So that's the whole concept behind therapy, for example, is that neuroplasticity enables changes in the brain that help to alleviate symptoms. Autism is a little bit different, though. Autism isn't just one symptom or one set of symptoms even. It's variable, and there's different manifestations of autism. There's different degrees of how debilitating it can be. Some people have autism, but they're very highly functioning. Some folks with autism, are able to, perform feats of intelligence that I could never do, and I don't have autism as far as I'm aware. And so, fundamentally, the answer to that question is yes. That for any kind of therapy to work, let's talk about a specific symptom of autism, which can be high levels of anxiety. For sure, like neuroplasticity would be the mechanism by which any kind of treatment, be it pharmacological, medications to help alleviate anxiety, or psychotherapeutic, going to a therapist and working through different sort of tasks and exercises to address that anxiety. Neuroplasticity is the system that would enable any kind of recovery to occur. Can nerve pain ever go away after breast surgery? K-Travel. So certainly if somebody's experiencing ongoing pain, chronic pain after a surgery, that they should definitely bring that up with their physician, either their surgeon or their primary care physician. Yes, but there's a bunch of different strategies by which you could accomplish that. And it really depends on what's causing the pain. If it's at the breast, or if it's somewhere else within the nervous system, and it's arising just because of some unintended consequence of the surgery. And so you said 6 years. Wow. Well, I would imagine you brought that up with your physician, and I mean they should be addressing that. Like, if they're not, then if I were in your position, and I'm not a medical doctor, I'm a PhD, I'm a scientist. If I were in your position, or if somebody in my family were in your position, I would say, and your physician has not been able to help you, I would say get a second opinion for sure. How many repeated thoughts create a neural pathway? That's an interesting way to put it. How many repeated thoughts? So neural pathway, when we use that phrase, neural pathways, generally speaking, what we're referencing is like a specific cluster of neurons over here sending signals to a specific cluster of neurons over here. They don't even have to be involved in thought. They can be involved in, like I referenced on the YouTube earlier before this, they can just be associated with like controlling the direction that your head is pointing, right? Or they can be responsible for enabling you to feel somebody like rubbing a finger on your arm. It's not necessarily a thought, right? It's a sensory experience, and so generally speaking, when we say neural pathway, we're referring to like an anatomical part of the brain, component of the brain. I heard neuroplasticity rewires the brain to make new connections and learn new behaviors in autism. Yes, for sure. Yeah, I mean, what I had previously just been speaking about, specifically working on, alleviating anxiety. But even outside of autism, right, or absolutely outside of autism, the only way that we can learn anything new is due to neuroplasticity, is due to neurons being able to generate new connections between each other or strengthen existing connections between each other, and getting rid of old connections that haven't been used for a while, or haven't been active for a while would be a better way to phrase it. So yeah, absolutely. Okay, what's the difference between a brain scientist and a brain doctor? Great topic, one of my favorites. So let's start with a brain doctor. A neurologist is generally speaking what you'd be referencing there. They get a bachelor's degree, go to college, and then they go to medical school and get an MD, a medical doctorate. And their training, of course, they're concerned with the same thing I'm concerned with, the human brain, but they're basically trained with all the information at their disposal while they're in school and after school. Armed by neuroscientists with that information, they're trained to recognize, problems that are occurring within the nervous system, not just the brain, but the whole nervous system, and then understanding what the most likely, what treatment would be most likely to be successful to reduce the suffering, right, or to cure the malady. So that's a medical doctorate. A neurosurgeon also gets an MD, a medical doctorate, but their training doesn't focus so much on those concerns, and they don't use things like radiology. They don't do like MRIs as much. I mean, I'm sure they can, but what their training is focused on is physically intervening within the nervous system to do things like remove a tumor, treat very severe epilepsy with lesioning very specific parts of the brain, those kinds of things. A neuroscientist, which is what I am, we get a different kind of training. We're trained to be scientists, and that training is really focused on, first, I mean, we all have to learn a lot about the nervous system, right? To be effective in any field, you need to know your field. But then where our training departs is in becoming very good at devising experimental conditions, right, or experimental design, to use a scientific method, to ask questions, and do our best to come to the most accurate possible conclusion, or reject the null hypothesis. And so our training is really focused on training us how to think scientifically, and how to scrutinize the science of others, and these kinds of things. And so medicine predates science by a long time, by thousands of years, arguably. Science in its earliest instantiation might have been called natural philosophy or something like that, but it wasn't really formalized as like a discipline until about a couple hundred years ago. And neuroscience is even younger than that. Modern neuroscience hasn't really existed for, people can make different arguments like, Ambroise Paré in France, or Andreas Vesalius in Italy. They were arguably conducting some very early neuroscience, but as a formal discipline, I would argue that it's about 100 years old or so. Okay, so there's all of that. Was there anything else? Oh, another thing is that it's also kind of a new development that medicine is actually science-based or evidence-based. Medicine was not always evidence-based, and it's kind of a recent phenomenon, like the turn of last century, sort of, where these, medical doctors were like, hey, those scientists tend to be pretty good at predicting whether something's going to happen. Why don't we start to work with the information they have? And ever since, there's been a lovely, friendly rivalry between the disciplines. I'm sort of kidding. Well, I guess I'm not really kidding. The sort of the most obvious example of when this kind of like intrudes on my life is when I see on like TV or something, some newscaster interviewing a neurologist or a neurosurgeon about some new finding in neuroscience. That's very frustrating. By the way, I wanted to bring this up. I was almost going to cover it on YouTube, but I decided to go with the computer brain artificial intelligence thing. There's going to be an amazing paper that's going to come out on Wednesday that basically focuses on the use of induced pluripotent stem cells, meaning stem cells, right? Stem cells, generally speaking, this is a category of cell that there's different kinds of stem cells, but they can become almost any other type of cell in the body, right? They can become a kidney cell or a heart cell or a skin cell, whatever. And one of the sort of the prime treatment targets of stem cells has been, for years now, Parkinson's disease, because Parkinson's arises from the progressive deterioration of a specific population of neurons within a specific part of the brain that produce dopamine, right? And that is largely what caused the sort of classic Parkinsonian tremors, the uncontrollable shaking. Well, there was a secret experiment that was basically done on one person who consented and funded the research himself. He himself was a former physician. A brilliant guy. I think his name was George Lopez. And he was developing Parkinson's disease. He had been undergoing all the sort of classic treatments, carbidopa, levodopa, just basically medications to kind of amplify levels of dopamine in the brain artificially. And he had heard about this stem cell research where they can take a cell from your skin and do what's called induced pluripotency. They can, put it in a stew with a bunch of other ingredients, and it causes those cells to de-differentiate back to stem cells. And the benefit of that is that they are your cells, right? They're not some other person's stem cells, because, a challenge with that is that your body or immune system specifically can come to reject the cells of somebody else, despite the fact that they're stem cells. So if they're taken from your body, that minimizes that likelihood very significantly. And it also improves the likelihood that those cells will be able to integrate into the body, and particularly in the brain, that's a huge factor, because if you just have neurons and they're not forming connections with each other in the brain, they might as well not be there. So it's a very, I could go on and on about this field. It's very fascinating. It's one that I definitely was considering going into. But the short story is about 2 years ago, this guy had millions of his stem cells essentially injected into the part of the brain that is among those that deteriorate in Parkinson's. This was 2 years ago. And they have just put out news articles that on Wednesday they're planning on publishing their paper to outline their results. Very cool, huh? Okay. Hey, what's up? How is information encoded in neurons? Great topic. In fact, it's the topic that I just talked. Well, part of the topic that I just talked about on the YouTube. You can find my YouTube by typing in like Ian Anthropoid Brain or something like that. And this recent video was about the differences between computers and human brains, or just neurons, nervous systems, in how they handle information. And so you can check that out if you're interested in that particular comparison. But part of it is that at a fundamental level, information in the brain is encoded by neurons firing what are called action potentials or impulses at specific speeds and at specific times, and sending those impulses to other neurons that then fire or don't fire and do the same, and on we go, neuron by neuron, to then make you crave some, apple pie or something. But so at a fundamental level, it is frequency and timing. Frequency of action potentials, how fast they're firing impulses, and timing, when they're firing impulses. And then I guess another one would be spatially. Where in the brain are those neurons firing those impulses, right? If the neurons are firing impulses towards the back of the brain, in the occipital lobe, in the visual cortex, you're probably seeing something or hallucinating maybe. Whereas if they're, in the temporal lobe, you might be experiencing some kind of memory, or you might be experiencing déjà vu. So yeah, that's the fundamental. And computers do not. There's a feature of how the brain exploits that system to be able to accomplish processing in a way that's far more efficient and far more effective than computers. Great topic. Question: if there is a physical difference in men and women's brain, couldn't trans people have opposites? So there are some studies that do identify. There's not a ton of research on this topic, but there is some. And there have been some studies that I've identified, and I'm going to try and remember the anatomical structures. Don't quote me. Forgive me if I'm getting these wrong. But I believe I recall seeing a paper that identified, like in a male who has transitioned to become a female, a part of the brain called the bed nucleus of the stria terminalis tended to exhibit the anatomy that would be more, that would be expected in the brain of a woman. And there are a couple other examples. So yeah, like you're on the right track. It's not like there is a categorically female brain and a categorically male brain, right? These are sort of very general differences that don't always hold up, and it's still sort of debatable as to just how different that anatomy is between the males and females, and whether they're functionally important, whether any of those differences, if they're there, have any sort of functional consequence. So any published articles, yeah, for sure, definitely that BNST paper was published and peer reviewed and stuff. This was a couple years ago, but I don't have them at top of mind, unfortunately. I'm sorry to say. How many books have you written? So I haven't written any books. I have written chapters in books, and I guess that's two chapters. One was on nicotine withdrawal, and the other one was on the role that a specific kind of neurotransmitter called a neurokinin plays in addiction and withdrawal. Okay, but I've also written other articles. 5G. Oh, thank you so much for the Super Hearts. Rainbow Patriot. Appreciate it. 5G effect on the brain. So it's been really interesting to watch 5G gain this sort of like notorious kind of presence in the popular mind. Here's the short story, right? There is no obvious evidence that 5G or Wi-Fi or Bluetooth or any of these points along the electromagnetic spectrum are meaningfully interact with biological systems, nor is there any feature of their physics that would lead one to believe that they would, right? for any point along the electromagnetic spectrum, either for us to be able to interact with it and be sensitive to it, either we have to have specialized proteins like on our eyes that are sensitive to the wavelengths in the visual light spectrum. It's the only way that we can see light. And it's very handy because the light, of course, moves at the speed of light, which is quite fast. And so it gives us a very up-to-date update on what's happening in our environment, because photons are constantly crashing up against everything, and so we can see those patterns of photons. But because we don't have any proteins that are sensitive to gamma rays, we can't see them, or X-rays, we can't see them. So there's that. And so either we have to have a protein, a specialized protein that's sensitive to some part of the electromagnetic spectrum, or the physics of those waves have to be such that they can interact with any biological system. Like I'm talking about the wavelength, like very fundamental physical properties. And when it comes to 5G or any of those adjacent electromagnetic points on the spectrum, there's just no reason to believe that would be the case. I can assure you, given all of the furor over 5G, that there will be studies. I mean, scientists will study this, so you can be sure of that. But I think if you were trying to find a neuroscientist who would anticipate, whose hypothesis would be that 5G causes some malady, some processing difference in the human brain, that journey would be difficult. They would be few and far between, and almost certainly not reputable. Finally, something interesting on Periscope. Well, thank you so much. I appreciate that. Okay, go stand under a cell tower. You go stand under a cell tower. Like, what? I would be happy to. I don't even know where the nearest one is, but I can assure you that living in Philadelphia, in fact, I don't think we can see it. In fact, there's a cell tower in the middle of Center City, Philadelphia, and so I'm almost certainly exposed to, I am inevitably exposed to cellular wavelengths. That's the only way that I can use cellular data on my phone, right? I would be happy to. So listen, as a scientist, like my worldview is not that I disregard any theory that comes from anybody who isn't like an Ivy League neuroscientist, right? That's not how I view science and reality. This is a hypothesis that a lot of people have come up with, that 5G is somehow deleterious to the nervous system, and some get even more specific on what those outcomes would be. Okay, that's a hypothesis. Test the hypothesis. Prove it, right? Just connecting dots, that's not science. That's just, theorizing. And that's valuable, but that is one very, very, very small part of the scientific process. So, if you are concerned about this, you develop an experiment to test your hypothesis. Okay, question. What are your thoughts on simulation theory? Are we Sims? Pranafins. So I have a friend who is also a scientist who also live streams. She's a cosmologist. Her name is Deanna Hooper, DC Hooper 91. And, she came to Philly a while ago. Gosh, I guess it was like 2 years ago. Wow. And, we talked about this. Like, I had a couple questions that I'd asked her in the past, like, hey, I keep hearing about quantum particles. People are interested in whether quantum particles play any meaningful role in the brain, in neuroscience. Her answer was no. And, I could get into that if you're interested. But so I asked about simulation theory, and, we couldn't really have a productive conversation because there's no, like, hard data, at least available to me, that I can understand, that can prove or disprove this theory. An important feature of scientific theories is that they are disprovable, or hypotheses is that they are disprovable. You have to come up with a series of experiments that would yield results that would ideally disprove your hypothesis. Prove why you're wrong, right? That's really what, as a scientist, what you're trying to do is, like, you have this theory, come up with experiments that would convince you that your theory is wrong. So when it comes to simulation theory, it just strikes me as being an unfalsifiable theory. Like, there's no way for us to really be able to prove that we are or aren't. It is possible. It is totally possible. And, I think, like, the way Elon Musk talks about it, that's, I think probably the best way to think about it. I wouldn't be as confident that we're in a simulation, but, like, given that it is imminently possible for humans with our computers to simulate realities, whether regardless of how complex or comprehensive those simulations of realities are, given that that's imminently possible, it is almost certainly inevitable, right? So that's attractive, but it's not enough for me to be like, oh, okay, so clearly we're simulations. Hey Asha, what's up? And hello Ibis, I see you're in here too. The brain is like a computer, right? Well, Pranafins, that was the topic that I just discussed on YouTube. So you can find YouTube, my YouTube. You can find YouTube by going to youtube.com/anthropoid. That's actually my channel, youtube.com/anthropoid. And I just talked about what it is, or one of the things, that is distinct between the human brain and how the human brain handles information relative to computers, and how computers handle information, and like some of the specific comparisons on which computers are superior to human brains, but then some, which I think are probably the most interesting and meaningful to us as humans, some that are that humans still dominate. And there's like a specific, at least one specific difference in how information is handled. That doesn't mean that computers will never be able to handle information in a similar way, right? But just as of today, they can't. But it is a good heuristic. Like it's a good metaphor. Because computers, particularly modern computers, like back in the day when computers were like kind of crappy, it probably was not the most useful comparison because they were quite simple. But now, given what computers can do, I think it's a lot more, and given the, availability of things, like machine learning, deep learning, what is it, like generative adversarial learning. Like there's a bunch of different kinds of machine learning that can replicate and surpass human cognition on very specific tasks. So given as those proliferate, we're probably going to be in a situation where computers will dominate us. Have you already answered a question about us living in a simulation? Yeah, I just did. Ian, does dexterity dictate fluidity of functional areas like Broca and Wernicke in the hemispheres? Does dexterity dictate fluidity of functional areas? I'm not 100% sure what you mean by fluidity. Like, do you mean like if somebody's left-handed or right-handed, do they exhibit more or less lateralization of language? So what this is referring to here are sort of the two classic language processing regions in the brain, Broca's area and Wernicke's area. And Wernicke's area is spelled Wernicke's area. But anyways, these structures basically control sort of two sides of the coin of speech, which is the production of language, moving the muscles in the throat, in the tongue, in the mouth to make, word sounds. And then the other is enabling us to form coherent thoughts and assign specific words to express those coherent thoughts. And when something goes wrong, like a stroke, that affects either one of them, you can see those discrete components of language deteriorating. Like, for example, Broca's aphasia is when somebody had a stroke or some kind of injury in the brain, and they can form coherent statements, but they really struggle in getting the words out. Just expressing it is almost impossible. And then the other kind of aphasia is where they can say words totally normally, but it comes out in a sort of word salad. And I've tried in the past to like mimic what it sounds like when somebody has Wernicke's aphasia. It's impossible. So I had to script it out. Like I had to write a script for me to be able to do it because it's so difficult to think in such a disjointed way. But that's because my Wernicke's area theoretically is doing okay. But I've never seen any evidence that lateralization, like somebody who's left-handed tends to have greater, Broca's areas in the left hemisphere have greater lateralization of language. But it's interesting, it may be, that research may exist. Have you answered a question about dreaming in the afterlife? I have not today answered a question about dreaming, but it's something I've discussed quite a bit. In fact, at length on my podcast called Wired to be Weird, on iTunes and Stitcher and Google Play and so on, Anchor. And dreaming is very cool. So dreaming used to come up like every single time, multiple times. And I always, my discipline within, I'm a circuits guy in neuroscience. I study networks of neurons, the functional properties, like what is it that these different regions of neurons that are talking to each other, what is it that they regulate? What is it that they enable us to do? And in my case, I was studying basically mood, anxiety, and how it sort of is the rudder of behavior. That's a very like bird's eye level of what I was doing, but you get the point, right? And I was also studying addiction and how anxiety and addiction are related. So I didn't expect dreaming to be very interesting. Also because, in neuroscience, when you're getting your PhD, actually in college, you learn about different theories of dreaming and, by and large, there's nothing that romantic about it. it's so enticing to think that dreams represent like our consciousness, subconsciousness trying to give us a message, right? But there's no reason to believe that. There are different theories of dreaming. But once I started doing a literature review, which means I just dive into all the research that has been done on dreaming, I found it to be a very interesting field. And because essentially when you're studying dreaming, you're sort of studying like the evolutionary history of humans, which is sort of like a cosmic way to put it. But dreaming arises, we think, because of a specific property of how what the brain needs to do to develop. Like to create all of the 86 billion neurons, and where they are and everything, there needs to be activity in the brain. And so dreaming seems to arise from spontaneous activity that's necessary for those connections between neurons to form, at least some of them. There needs to be just some spontaneous activity before you're even out of the womb for those connections to be formed. And then after you're born, it's not like people who wouldn't have dreams would be more likely to reproduce or survive, in the wilderness or whatever, and so there's no selective pressure. There's no reason for us to have to get rid of dreaming, and so we just keep going. Can I connect with you on LinkedIn? Of course, yeah, I'm on LinkedIn. Love from the UK, love from the US. If you add REM sleep and deep sleep totals and get 4 hours, will you feel rested? That's an interesting. If you add, if you just get 4 hours of sleep. Probably not. I mean, so different people have different chronotypes, which is a lovely word that I learned recently, meaning like there do seem to be some genetically determined predispositions to whether you're a night person or a morning person. I am a night person. My entire family are night people. It is a daily struggle because the world was built by morning people I just cannot understand how their brain works. But similarly, different people will derive the greatest benefits from different durations of sleep. In other words, some people can get by with just 4 hours of sleep and be just fine, whereas other people, need 7 hours or longer to feel optimal, right? And in fact, there have been some studies of people who people in like disciplines that tend to request short periods of sleep, right? So like nursing, nursing, particularly like emergency room nurses, that is an extraordinarily high pressure field. Even within medicine, it's among the highest pressure, and nurses are essentially like always on. And this was like a classic study. It was shown that nurses tend to do just fine with like 4 hours of sleep. And the way they would measure it is like they would give these nurses like a cognitive test, reaction time, these kinds of things that are sensitive to whether you're sleepy or you're fully awake. And so, yeah, there's variation there. So I can't tell you for sure, but almost certainly, by and large, 4 hours of sleep is not going to be enough. Certainly not for me. Actually, that's not true. If I get 4 hours of sleep and I'm free to wake up late, I am fine. It's just, you can't do that. Do you have a YouTube channel? Yes, I do. YouTube.com/anthropoid. The easiest word to spell in the English language. I didn't pick that word with the intention of talking about science, but you can also just type in like Ian Neuroscience Brain or something like that. Ian Anthropoid Brain. And you can find the way to spell anthropoid by going to my handle either on Twitter or on Periscope. What are your thoughts on Elon Musk? I think he's a really interesting guy. I obviously don't agree with him on everything, but I don't agree with my wife on everything. I think that where Elon Musk's activities sort of overlap with mine the most is in his company called Neuralink, which is a whole brain computer interface company. When it first came out, I think pretty much everybody, it sort of came out before he had developed that kind of highly notorious kind of internet presence. I mean, he sort of had, but it was more like Elon Musk is like the new Iron Man, or the real Iron Man. But despite that, even then, I think a lot of people in neuroscience were like, okay, buddy, sure. But then later on, it was shown the people that comprise his board of directors are like heavy hitters in neuroscience. They're no joke. They're real accomplished neuroengineers and neuroscientists. And some of them had been working on different potential technology platforms that would enable a whole brain computer interface, meaning that a system, whether it's an array of electrodes or a network of electrodes or tiny little, almost microscopic electrodes that are wireless, that enable a computer to interface with a majority of the brain, if not the whole brain. Neural lace, neural dust, these were different sort of technology platforms. And fairly recently, I don't even know what time is anymore, but he did a sort of demonstration of Neuralink, the status of it, and pretty much the reaction, my anticipated reaction was going to be, it's going to be nonsense, right? But pretty much everybody in the field that I talked to, particularly the neuroengineers, were like, this isn't really that new. Like, this technology is not that new. And so it seems like they're sticking to something that's viable and realistic, which is very, very exciting. I mean, I welcome the day where we can integrate technology into our nervous system to amplify human consciousness. Apart from that, I mean, I think that he tends to be rather arrogant in certain fields, just, particularly when he's talking about COVID-19. But I imagine that you kind of have to be to do the kinds of things that he does. I remember we had a conversation about that. Yeah. How am I a troll? I don't know. Maybe we're born that way. Technology is enslaving us. What are you going to do about it? Hi, Viborkin. I am not going to do that. Or I'm not going to do much of anything. Yeah, I mean, I imagine that there are opportunities for people more like psychologists and folks like that to devise recommendations to sustain your discipline when it comes to technology. But I mean, listen, I agree with you in that a fluency with technology is necessary to really operate most of the modern world. And so I wouldn't call that enslavement, though. I would call that symbiosis. Okay. Do you think Neuralink will benefit us? Do you think it would have an effect on gaming? Yes and yes. So on YouTube, I talked, again, a little bit about the differences between computer systems and the human brain, like how computers manage information and signals versus the brain. And computers are better at certain things, much better at certain things than human brains are, right? So, for example, they can operate a level of precision that is significantly higher than the human brain, right? In the short way to put this is like to handle a number that has like thousands of digits, right? To accurately reflect, let's say, the size of, I don't know, the circumference of a certain widget, whatever. We can't like operate handling all those digits. We have to round until we get to a number that's like reasonable. But computers, they can do thousands of digits and get extraordinarily accurate representations of whatever it is that they're trying to compute. Human brains can't do that. Also, computers have superior memory than we do, right? They have almost perfect memory. Human memory is notoriously, frail, unreliable. I mean, it's wonderful that we have it, and it is, magnificent, a wonder of evolution. But it is, subject to, it's fallible, right? So there's those kinds of things, and so with the advent of whole brain computer interfaces, we could exploit that superiority that computer systems have, and again, symbiose. I don't think that there's a verb form of symbiosis. Anyways, we could form a symbiotic relationship with computers, and the whole sort of motivation behind or behind Neuralink is to enable humans to compete with artificial intelligence. Because as I said earlier on in this conversation, there will come a time when artificial intelligence surpasses human intelligence. Okay, I realize that I'm missing. Hi, interesting your touch on quantumness in the brain. What is your general interest thoughts on staying in classical world theories or quantum world theories in your work? Yeah, I mean, so I sort of hinted at this, but I'm sure that there are neuroscientists who concern themselves with quantum mechanics. I'm sure, but I've had conversations with Deanna, but then other physicists as well, and just been like, they work in experimental or theoretical physics, and so I asked like, hey, should I be caring about quantum particles, and they were like, quantum particles are incredibly important for a lot of the world, but generally speaking, and this is my perspective on it, like the brain is a very complicated system that has a bunch of functions, and generally speaking, the meaningful operations, the meaningful like action potentials or neurotransmitter release, they're operating at a level of physics that's like big enough that all that quantum uncertainty and things like that are restricted enough to not generate meaningful consequences for consciousness. I could be wrong. Again, I'm not a physicist, but so I don't really concern myself with those questions. It's sort of like if your task is to understand to understand the consciousness of an elephant, and instead of looking at the brain, looking at the anatomy, doing electrophysiology, recording from neurons, seeing what they're saying. But instead of doing that, what you're going to do is study the physics of how the hairs on its legs form. It's like, it's important to understanding an elephant, of course. But if you want to understand consciousness, it's just not really the domain of physics that is going to yield the most meaningful answers. Could be wrong. Could totally be wrong. Okay, can you please answer my question so I don't have PTSD? Smiley J. I'm not trying to know about a computer. I'm trying to know if I got PTSD from that traumatic, scary, Listen, I can't tell you. I mean, if you are sincerely concerned that you have PTSD, you've got to talk to a therapist. Talk to a physician. Yeah, I mean, is it possible? Absolutely. If you've had a traumatic experience, of course it's possible to develop PTSD. Okay. So it's kind of hard for me to help comfort people when they are sad. Does that mean my brain has low levels of sympathy? That's an interesting question. I mean, not inevitably. There are variations in how empathetic people are, like in how much, how significant of a reaction people exhibit to seeing somebody else suffering. So that you can think of it as sort of like a spectrum of empathy, where some people are extraordinarily empathetic and like they almost literally feel the pain of somebody starving or the pain of being punched in the neck. Whereas on the other end of the spectrum, you have what might be classified as like psychopathy or sociopathy, where there's just zero reaction whatsoever. So yeah, I mean, but when it comes to like comforting somebody else, that integrates more than just empathy. It integrates past life experiences, the way you were raised. Not everybody is comforted in the same way. Like if somebody's sad, some people might want to get a hug. Some people might hate getting hugged, right? And so it's just a little bit more. I wouldn't resign myself to being a psychopath if I was bad at comforting people. All right. Do you think the next few years we'll be able to travel to Mars? Yeah. Well, the next few years. I mean, I don't know. I know that NASA's working on it, and given the sort of expedited presence of certain private sector entities like SpaceX, and I mean I believe SpaceX specifically is designing in anticipation of going to Mars. Like they've always wanted, or he's always said he wanted to do that, but I think they're like actually doing it, like building the prototypes. But whether that's going to be in the next few years, I don't know. I'm sort of skeptical in general that of progress in the next few years. But yeah, I mean, we certainly have the technology. It's just whether or not it's going to happen. And that's probably a question that would be more optimal for somebody who is involved in astronomy or something like that. Would brain transplants ever be possible? So the short answer is yes. But that is a criminally short answer, because the longer answer is yes, but not anytime soon. The reason that oh look, it just came in, DC Hooper 91. So DC Hooper 91 is a cosmologist, and questions about things like quantum mechanics or simulation theory or travel to Mars. She would be a far superior source of meaning or of nutritious answers on those topics. All right, the Artemis program is a stretch to go to Mars, in addition to the Falcon Heavy rocket by SpaceX. Right. Good evening. My pleasure. I hope all is well with you, Deanna. Hope you're staying safe and healthy. I mean, imagine you're more likely to be staying safe and healthy where you are than where I am. Okay. Brain science. Can you explain my condition, which is synesthesia? Oh, yes. Okay, so brain science is what it's a term that means exactly what it's supposed to mean. Neuroscience can be confusing for some people, and so I just say brain science because that's really what it is. So synesthesia is an extraordinarily interesting condition. For anybody that's not familiar, synesthesia describes a condition wherein sensory modalities are crossed, where somebody, for example, will hear colors or taste sounds, or certain, and so the point being, it manifests in a bunch of different ways. Right? There's different kinds of synesthesia. Like one of them is I think grapheme color, where like letters and numbers will be associated with some specific color. So whenever you see or hear the number 4, you experience green. But then there's sound to color. In fact, one of my good friends growing up in high school, his dad was a conductor, and he had sound to color, where synesthesia, where if he hears specific sounds, his visual system becomes influenced. But there's a bunch of other forms of it. I thought green. I have sound to color. Oh yeah, interesting. Yeah, and it was kind of an issue for him because like he first of all, it sounds like a superpower to me. Like it sounds so cool, particularly if you're a conductor, right? Like when he's writing music, he's painting music. Like how amazing is that? But of course, when he was driving, he had to be extraordinarily careful because it could be quite distracting. Where am I? I'm in Philadelphia, my beloved Philadelphia, the best city in America, the heartland of America. So first of all, so the short answer is we don't know precisely how it is that synesthesia comes about. There are different theories, however. So, and you can sort of bucket these theories into 2 general buckets. One is the proximal theories, which is basically like, different regions of the brain are responsible for processing different components of your sensory experience. So one part of the visual cortex is devoted to color. Another part of the visual cortex is devoted to decoding movement. So if you're seeing like a green, diagonal line moving across your screen, different neurons are breaking that down in different ways. Similarly, different parts of the auditory cortex break down sound, enable you to make sense of sound. And by the way, the brain devotes a large bit of real estate to visual processing. Something like almost 1/3 of our brain is devoted to vision. So it must be a very evolutionarily useful thing to have. Anyways, so the proximal theories of synesthesia are that literally neurons are adjacent to one another, or close enough to one another that, unlikely, but in some cases, connections will form between them, meaning that when a neuron that would be, activated when you hear a sound is activated, then by sort of happenstance, by chance, those signals get conveyed to visual parts of the brain, and so you experience a visual experience, and that doesn't happen in the vast majority of people, but in some cases it can. So that's like, you could call that like the proximal theory of synesthesia, or one of them. But then there's distal theories as well, where there's like perhaps genetic explanations for how synesthesia comes about, where what's interesting about synesthesia and genetics of synesthesia is that it does run in families. So there does seem to be a genetic component to synesthesia, meaning that if your parents have synesthesia, you are more likely to have it. Not inevitably, but you're more likely to have it. But what's interesting is that the particular synesthetic associations do not run in families. And so they might have, sound to color synesthesia, and you inherit synesthesia, but instead it's like lexical gustatory, where like, you read or hear a word and you experience a flavor. So my father is colorblind, but I have synesthesia. Oh, that's very interesting. I mean, right. So there's some interesting feature of probably the genetics of your lineage that encode your visual system. And so, it might just be a little bit more of a volatile developmental process. And so whereas, color blindness can emerge, and there's different kinds of color blindness. Similarly, there might just be some sort of
a volatility at a developmental stage encoded by the genes you've inherited that make the brains of your lineage more likely to have some interesting features of the visual system that are far less common among people outside of your genetic ancestry. But really cool. I think I did a podcast on synesthesia, I think. Okay. You're great. Thanks and bless you to broadcast. It's my pleasure. Thanks for coming by. Okay. How does the brain work in polyglots? I'm not sure that I could come up with a satisfying neuroscience answer for that. Okay, home of the Philly blunt. Yes. Too late in the evening for me. Maybe within the next week. Oh, cool. Okay. All right. You should make brain and mental health treatments and supports mandatory on NHS as a matter. Does the NHS not treat mental health? I would be surprised if that's the case. I mean, I don't live in the UK, but I would be surprised. All right. Oh, jeez. Okay, appreciate your thoughts, and that makes sense. I mean, not in the quantum superposition sense, but right. Yeah. Okay. Do you think? Oh, yeah, right. So, do you think Neuralink will influence gaming? Absolutely, no doubt. So on the podcast, I did 2 episodes devoted to whole brain computer interfaces and Neuralink. Not specifically Neuralink. I mean, I do talk about Neuralink specifically, but more, I just use it as sort of like a framework to explore whole brain computer interfaces. But one of the things that we do in my podcast, which was a very fun exercise, was come up with ways that, like, what it would be like to use a whole brain computer interface. And so, for example, I go into a premise where you're working and you have the Neuralink, whatever the system is, and again, that's years and years off. Like, this is not going to be a reality for a long time. But let's say we have it, and you're sitting at your desk, if that's how we work in the future, and rather than having a cellular phone or a smartphone, vibrate when you know that you have a message, you just have an intuition that your loved one needs you or wants to talk to you. And not only do you just have the intuition, like, oh, sounds like my wife needs me, but you even get a sense of what kind of need it is. Like, is it because she's hungry? Is it because she's angry? Is it because she wants to go out on a walk or something like that? And there's no sort of bandwidth limit, right? It's not like you need to read the message, you just sort of receive it. So that's one example. Another is like, okay, let's say your loved one went on a vacation, wherever, to Mount Rushmore or the Grand Canyon or whatever, and you couldn't go because you needed to stay and work or whatever. And so, your wife or your husband or whatever is walking, and they come up, to this incredibly beautiful visual experience, and they want you to be a part of it. And so they can just immediately, bop up a little like picture-in-picture type of situation where like only part of your visual field is devoted to, seeing what she's seeing. And then you could say, take me there. Like, she could offer, okay, you can now assume the entirety of my visual experience, and then you just sit back, and then your entire visual experience is now controlled by what your loved one is seeing. So it's like VR, but there's no interface, right? It's just happening to you. Okay, so and so for video games, I mean, you can imagine how amazing that would be. But there are some nightmares that we could discuss as well. So, for example, in terrorism, right? So if you had the whole brain computer interface, right? It is fundamentally a computer system that has to operate with some software at some level somewhere in the world, whether it's a little pack that you're wearing, or whether it's like servers in the cloud in the catacombs of Amazon or whatever. So like all computer systems, they're vulnerable to being exploited by bad actors, nefarious actors. And so as a result, because the whole brain computer interface theoretically is a whole brain computer interface, meaning that it's interacting with all parts of the brain, not just your visual system, not just your whatever, your memories, but all of it, they could hack the system and gain control of your voluntary musculature. In other words, they can control when you move your arms, literally turn you into a robot. But not only that, like, okay, and so then they could, control you such that they force you to devise a bomb and then blow it up somewhere. That's one example. But perhaps even more nightmarish would be they don't even need to do that. They can just plant in you the desire to do it. They could make it so that every time you commit a terrorist act, you have the most significant orgasm you've ever experienced in your life, right? That's a pretty big incentive, right? Or, it could just be that the only way that you derive pleasure is by inflicting harm on the people around you, right? These are theoretically possible. They're as possible as, being able to assume the visual experience of your loved one when they're at the Grand Canyon. So yeah, I mean, it's sort of, this is all very theoretical, right? Because we're not even close to the basic necessities for a whole brain computer interface. But it's not like there are some magical limits to our capacity to accomplish this. And, it's just physics. So yeah. What is going on when you're having a lucid dream? Really interesting topic. And we talked about that on the podcast called Wired to be Weird on iTunes and Stitcher. Lucid dreaming is very interesting. So there has been some research on lucid dreaming. Generally speaking, okay, so first, let's start, what is a dream? We think most dreaming occurs during a phase of sleep called REM sleep, rapid eye movement sleep. It's when, that was weird, it's when activity in the brain while you're asleep tends to resemble that of waking life, with one very important exception. There's greater activity in the frontal regions of the brain, particularly the prefrontal cortex. Prefrontal cortex is one of the most quintessentially human parts of the brain. It's what enables us to behave with greater forethought and planning than other animals. Well, it's not the only thing, but it's one of the things. So when you're sleeping and dreaming during REM sleep, activity in that part of the brain tends to be suppressed. However, every now and then, for one reason or another, activity begins to crank up, and all of a sudden you are, and so we don't know precisely what that's doing functionally. But there have been, a handful of studies that scan the brains of people who are dreaming and then report that they lucid dreamed, and there tend to be elevations in activity in frontal regions of the brain. Now, it's not a stretch to speculate that a byproduct of that elevation in activity in the prefrontal cortex would enable somebody to scrutinize a dream in a greater way, to a greater degree than they would without the activity in that part of the brain. And so that is, I think, the most convincing model to understand lucid dreaming that I've seen. All right. Doubt it. Wait, do you have a girlfriend? I have a wife. Thank you for asking. You're speaking so fast. Yeah, sometimes that happens. Sorry about that. You reminded me of the movie Brainstorm, where neuroscientists record visual perception before death. Oh, interesting. I haven't heard of that. There are projects, I'm sure you've heard of this, but projects basically trying to decipher a visual image that somebody's looking at by using, it was like a combination of EEG and something else. Or maybe it might have just been fMRI. This was Jack Gallant's lab. And they could basically, so they're showing somebody a picture, they're staring at that picture, there's activity in the visual cortex, of course, and then they scan occipital activity, and they were able to just using the activity in that they've recorded, they were able to recapitulate a very crude form of the picture that the person was looking at. It's pretty cool. Does IQ come from genetics or the individual? Well, what's the difference? Your genetics are just as much a part of you as your life experience. But so this is a contentious debate within neuroscience and intelligence research. It's worth noting that intelligence research predates modern neuroscience, so people have been trying to ask and answer these questions for much longer than modern neuroscience has really even been around to contend with this question. And I only bring that up because the reason that, so early on, let's say 10 years ago, 15, 20 years ago, it was far less contentious. the sort of the accepted wisdom was that IQ is largely, if not entirely, genetically determined, and there's really not that much you can do to move your IQ either up or down. It's just sort of like a constant of, your brain. That was several years ago. However, more recent research has revealed that this is a far more nuanced feature of human consciousness, but also a question than researchers had really initially appreciated. And by integrating more sort of sensitive, like essentially controls of environmental variables, somebody like Elliot Tucker-Drob down at UT Austin, I think, still, I say still because I always forget to check where he's working now, but his research has shown that no, actually IQ is quite a bit more variable than we used to think. And using sort of classic genetic techniques like twin studies, identical twin, fraternal twin, dizygotic twin studies, and comparing, so genetically identical, largely or much more genetically identical and identical twins, more genetically identical than typical siblings among fraternal twins or dizygotic twins. And then just normal siblings who are, again, more genetically similar than people who are unrelated. By looking at sort of IQ trends among all those different populations, and then also environmental features like their socioeconomic status. Identical twins that got separated at birth, one of whom was adopted by a wealthy family with a lot of resources, another by one with lower resources. What happened to IQ? And then timing in life plays a significant role, timing in nervous system development. All of this to say, IQ, first of all, it's not a truly comprehensive measure of human intelligence, despite the name, intelligence quotient. But it does measure important parts of human intelligence. That's one important consideration. But the second is genetics absolutely play a role. They play a role in everything you do, essentially. But as the years have gone on, and more recently, researchers have shown that the role of the environment is significantly greater than we thought. My IQ is 240. Wow, it must hurt. Okay, how can I make myself not as dumb? First of all, I would recommend that you don't think of yourself as dumb. You're not dumb. Very few people would be objectively and universally considered to be dumb. But if you conceive of yourself that way, then you're probably it's a self-fulfilling prophecy, right? You're not going to engage in activities that you might associate with people who are smarter than you, just like reading books or things like that. If you think you're dumb, then you're not going to do it. The best thing to do is expose yourself to new information with which you disagree. What scientists do is we get very, very, very knowledgeable about a very specific domain in science, sometimes even sub-disciplines within domains of science, and you become an expert on that. Then you can look much smarter than you really are, like I do. So develop expertise in something that is remunerative or lucrative, or that is some form of specialized knowledge, or just expose yourself to a lot of different information, and be passionate about it. Really want to learn, And one of the exercises that I think is really good that I'm definitely going to be imposing upon my daughter is, do you believe in evolution? She will know the right answer from my perspective, but then I'll ask her, okay, prove it. Why do you believe it's true? That's a great exercise, because if you can't really explain why it's true, then do you really know that information, or are you just accepting it? I think that's a pretty useful technique. You have a daughter? Yes, I do. And she is so adorable, I cannot communicate to you. What happens to our brain when we are exposed to something we disagree with? That's a great question. Okay, there's a bunch of different aspects of this, but one thing that will almost certainly occur is elevations in activity in the insular cortex and the amygdala. And depending upon the degree to which the insular cortex reacts, reacts to this disagreement, you may have greater or less revulsion at this repulsive idea. Like, for example, politics is like such an obvious example of this, because these are like the features that govern our daily lives. But whatever, like somebody arguing to you that like they believe that God exists, or that they believe God does not exist. For a lot of people, some people, or probably a lot of people, seeing the arguments with which they disagree on that topic, on such a personal topic, can be not only like, hey, I don't agree with that, but also repulsive and like almost insulting. And so there will be reactions in the brain that resemble what happens in the brain when something, very simple and repulsive occurs. Like if you're walking by a rotting carcass, or if you're walking by a dumpster that has, rotting food in it or something. That's a very similar process is occurring when you're like, that is repulsive, gross, I need to get away from this, it's a danger to me, right? If you think about the evolutionary history of that, the reason that things smell good or smell bad is because evolutionarily speaking, generally speaking, things that smell bad probably have pathogens in them, right? Of some kind, bacteria, parasites, things like that, that could then threaten your life. And so if you just have this reflexive revulsion at this disgusting thing, you are much less likely to eat it and probably avoid it. So a similar process is occurring in the brain when you come across a worldview or a concept that you find disagreeable. But that in and of itself isn't like nutritious, but it is a good cognitive exercise to go and sort of methodically think about why you disagree, right? Not just I disagree because it's what I believe, but like, let's look at their arguments and come up with my counter arguments. Like that is a positive exercise. And like oftentimes, one of the things that has been associated with increased risk of dementia and earlier onset of dementia is a lack of cognitive challenge. And generally speaking, in science, what has been used is like people who stay in school for longer, they tend to have slower onset of dementia or lower onset of dementia. But it's not that school itself, just being in a classroom, is a therapeutic thing. It's just that's an easy shorthand for, generally speaking, if you're still in school, you're challenging yourself cognitively. But you don't have to be in school to do that. And so, exposing yourself, doing that kind of, that meticulous, argument evaluation can be beneficial. Okay. Great topic. So the mental equivalent of stepping on a dead cow. Yeah, pretty much. I mean, it's repulsive, right? And it's a survival mechanism. But it's not, the brain is a very, very messy organ. It is absurd, in its anatomy in some cases, where like, let me think of so the septum and the stria terminalis. Well, anyways, there are two regions, it's subcortical regions in the brain that are literally right next to each other, like adjacent, right next to each other, and they communicate with each other. You would think, oh, hey, it would be very effective or efficient for this brain region to just send projections right there to the brain region right adjacent to it. But no, actually, it sends its projections all the way around this long, circuitous pathway to then reach its adjacent neighbor. Right? That's an absurd way to design anatomy, right? And it almost certainly arises from a specific developmental step that occurs during the development of the nervous system, where either these brain regions are actually much further away, and then eventually they migrate to each other, or whatever, or there are connections along the way that need to happen. But the point being that the brain is not a perfect engine of consciousness, and in fact it's rather messy in a lot of cases, and so it's not like the brain evolved intentionally to enable us to have conversations about the brain over hundreds of miles, or we're certainly not perfectly rational creatures, and so the brain really hasn't changed very much, or we have no evidence that it's changed very much in the past several thousand years, 10,000 years, 50,000 years. And so as a result, and it's not like humans, let's just say 2,000 years ago, it's not like, they were interacting with each other, communicating with each other in nearly as many ways as we are. And so we're basically using this ancient organ in a completely disparate context, modern society, And we're fortunate that we're able to exploit these systems that were really sculpted by natural selection, by the need to get resources, by the need to reproduce, by the need to avoid damage, either pathogenic damage or physical damage. And so we're using all of that machinery that was really sculpted by those fundamental forces in a modern context. And that's why when you see somebody say God doesn't exist or God does exist, you have this kind of reaction. Even, you don't manifest that, exhibit that behavior, but inside that feeling is a direct cousin to the feeling of your, ancestors eons ago who were walking by a dead carcass and thought it smelled disgusting. Could brain disorders like schizophrenia ever be completely cured? Yes. That's the short answer. But the longer answer is that, particularly with schizophrenia, which is a very, very multifaceted condition, it's very complicated. And the reason I say that is not everybody with schizophrenia exhibits the same symptoms. Some people exhibit more positive symptoms of schizophrenia. Some people exhibit more negative symptoms. Positive symptoms are things like the hallucinations that I think most people classically associate with schizophrenia. But not everybody has the same kinds of hallucinations, right? Some people have auditory, more frequently they're auditory hallucinations, they're hearing things that aren't there, but some people have visual hallucinations. Others don't have those, and all they have is just an elevation of paranoia, disjointed thought, weird beliefs, anxiety, these types of things. And so, I almost joined a lab at Tulane University in New Orleans. The lab was somebody who was a schizophrenia researcher, and I remember having a conversation with her. By the way, for the interview, that interview weekend, it was during Mardi Gras, which was wild. I had no idea until I landed that oh, whoa, wild. Anyways, there is this sort of anticipation, and this is true for autism as well, that as we learn more and more of the granular details of the genetics and the neurobiology that underlie the unique components of the brains of people with schizophrenia or autism, we'll begin to parse and disaggregate some of these conditions that are extraordinarily similar but consistently distinct. I'll give you a very concrete example. So for a very, very long time, there was a subset of girls, almost exclusively girls, by far mostly girls, who would be diagnosed with autism. They would develop totally normally for 2 years. No different than anybody without their unique biology. And they would even begin to develop speech. My daughter now can say well over 100 words, and she's stringing together words. So adorable. And then she'll fill in the gaps between words, but it's just gibberish. It's very cute. Anyways, so these girls would look just like my daughter, who knows how my daughter's going to develop, but and then after about 2 years, they develop speech and everything. They begin to deteriorate, and they begin to lose language, and this can happen at different speeds, but over time, they lose the ability to speak coherently, and then there are specific physical abnormalities that emerge. In some cases of autism, repetitive movements is a sort of classic symptom. There can be different repetitive movements, but in this particular subset, again, these girls develop normally for 2 years, etc. They have a very specific stereotypy, a very specific repetitive movement, and it's hand wringing. So this is their repetitive movement, and it's consistent. For the longest time, scientists assume that this is autism. It's just there's something consistent about the biology of this kind of autism that makes it so that these girls are so similar to each other. And it turns out that yes, indeed, this is now recognized as Rhett Syndrome. And Rhett Syndrome is one of the very, very few conditions that arise from a change in just one specific gene, MECP2. And so there's been a sort of ongoing debate as to whether or not Rett syndrome should even still be considered under the umbrella of autism spectrum disorders. And that it sort of doesn't really matter. What's important is that that is an example of as we learn more and more about schizophrenia, about autism, about bipolar disorder, about psychiatric conditions in general, we'll likely come to a point where it's like, this is maybe autism spectrum disorder type 1A or whatever it is, and so the point being that different treatments will be optimal for different subsets of those conditions, meaning not everybody who is somewhere on the autism spectrum, or not everybody that has schizophrenia has the exact same biological, unique biological features that land them there, and so therefore different treatments will be suitable. So yeah, that's a very long answer, wasn't it? Jeez. Is mal debarkment syndrome treatable? I'm not familiar. What is going on out there? I'm not familiar with that condition, I'm sorry to say. Why do some people get migraines often? Does it have to do with what we eat or drink? A woman of valor. It can, yeah. So first of all, we don't know all the causes of migraines. Actually, there was an article that just came out. Can't remember. That basically honed in on a specific biomolecule that is elevated in people suffering from migraines. Some people suffering from migraines. It's not the first study like that's come out, but it is another one that's come out. And so it seems to be the case that there's like a whole constellation of molecules, within neurons, or not within neurons, within cells that are near pain receptors, nociceptors, that for one reason or another, perhaps genetically, they become irregularly elevated, and that causes pain, despite the fact that there's no underlying damage that's producing the pain. In other words, it's not like a migraine. A migraine is not a sign, very, typically, that there's some kind of damage occurring in the body. It is just a sort of artificial source of pain, but it's extraordinarily debilitating. And so there, some new treatments have come out for migraine that are pretty exciting, that target those specific biomolecules. But anyways, yeah. So some people have, for example, genetic. They're less capable of breaking down certain amino acids in food, and so as a result, those amino acids circulate through the blood and then reach the brain, and then can cause sort of hypertension and these types of things. But generally speaking, like for a true migraine, and then of course sensory experiences can be associated with a migraine. The connections between those, I don't think we have answers for the mechanisms that would connect a phenomenon that's occurring in the brain, a sensory experience, and a pain experience, because within the brain there are no pain receptors. Pain is made coherent within the brain, meaning like you are only sensitive to pain because you have a brain, but the actual mechanisms that detect the things that cause pain are not within the brain, they're outside of the brain. Not always the cause, but there are a lot of foods that trigger my migraine. I didn't know you got migraines, Deanna. Interesting. What are good brain exercises for delaying dementia or increased memory? Any apps you recommend? So my shop, it's funny, like, so there's probably one app that everybody would think of that was advertised so heavily, like a couple years ago. If you were asked, like, hey, do you know of any brain training apps? You'd probably bring up Lumosity. And I remember the commercial you would see was that there's like this very lovely woman who said, and it's based on neuroscience. And it's like, that's like a meaningless statement. It's like the spaghetti I cooked last night was based on neuroscience. Anyways, so some of my friends here at the University of Pennsylvania, they're cognitive neuroscientists, meaning that they are concerned with the sort of the outputs of the brain. They're concerned with, sort of very broad anatomy, anatomical regions, and that's pretty much as opposed to like nitty-gritty anatomy for me. Nitty-gritty anatomy, which is what I concern myself with. They did a study. They didn't say that they were studying Lumosity, but they were. But basically, they were evaluating whether or not these cognitive training apps actually yield any measurable changes in cognition or cognitive performance. The answer, to our surprise, was no. They couldn't detect any change. And so I say that it's surprising because I think pretty much anybody in neuroscience would agree that exposing yourself to cognitive challenges in general yields benefits. And as I said earlier, one of the things that is associated with slower onset of dementia, later onset of dementia, is continuing education. Again, doesn't mean that you have to be in school for that. You just, people who continue exposing themselves to new information, learning new information, forcing their brain to solve new challenges, that tends to yield benefits in the context of dementia. So unfortunately, there's no like specific set of exercises that I've seen that is actually beneficial. That it's consistently beneficial in that way, nor like uniquely beneficial in that way. Like if you do Sudoku followed by a word search followed by, multiplication tables, like you will, you'll stave off dementia by 5 years. There's no such a recipe. But more broadly speaking, just forcing yourself to continue learning new things, and by that I don't mean just like reading books about topics that are widely focused. Like again, I always say this, like learning how to dance. I only say that because that's how I met my wife, but that's how I met your mother. Learning how to dance, learning a martial art, learning a musical instrument, learning how to speak a new language. That one's really good. All of these things are useful because you can now do those things. Particularly if you learn a new language, but also that is the kind of like forcing your brain to solve new challenges that is sort of like an example of that continuing education. Now, of course, this is different for like stroke-related cognitive challenges because when it comes to stroke, you can, depending on the severity of the stroke, but you can really hone in on specific regions of like where in the brain where the stroke has occurred. And so that's different from like dementia. Dementia is a more global kind of breakdown in communication between different regions of the brain. So it's a little different. Hello, Upndegler. Upndegler. Hello. Taking golf lessons? Sure, yeah. I have, okay. What about people seeing ghosts? Can that be explained as hallucinations in the brain? Ghost man with 5 sixes. Interesting you didn't choose 3 sixes. So certainly sometimes, like, far be it from me, or it's impossible for any scientist to, with, certainty, conclude that every time anybody's ever said that they've seen a ghost, that it was a hallucination, right? That's like an absurd, that would be an arrogant statement for a scientist to make. However, it's not arrogant to suggest that at least some of them absolutely could be, for sure. And we know of some particular examples of visual hallucinations that are sometimes attributed to ghosts that are consistent and totally explainable. And that is, hey, what's up, Illuminati God? And that is hypnagogic hallucinations. Or, this happens oftentimes or sometimes when people have sleep paralysis, where they wake up, they're sort of pseudo-conscious, but part of their brain is still in sort of a sleeping state, and they're paralyzed because one of the things that happens to prevent us from getting up and sleepwalking and exhibiting REM behavioral disorder is our brain paralyzes us. And when that paralysis is insufficient, people do get up and walk around and sleepwalk and stuff like that. I have a great video of that on my website of REM behavioral disorder, where there's a dude who's deeply asleep, right? And he's just sort of like sitting back on a bed, and it's sort of far away, so you can't really see his face. And he's just sort of like, very casually, like, flicking a cigarette. It looks exactly like he's smoking a cigarette, but he's totally asleep. And he has REM behavioral disorder, and that's because that paralysis has not been instated by the brain when he's asleep. Anyways, sometimes when people are trying to wake up, they exhibit the sleep paralysis, and they experience hypnagogic hallucinations. And what's further interesting is that there are consistent hallucinations to that sleep paralysis, one of them being the intruder hallucination, where they feel as though there's some entity, somebody, some thing that is near them in their room, preventing them from moving. Sometimes even there can be a sensation of like pressure on the chest because that entity is pushing on the chest or sitting on the chest. But it's a complete hallucination. There's even like there's one that's like the old crone, where people see like a sort of just a witch, essentially, like a scary elderly woman, malevolently looking at them, and it's a total hallucination. So at least some of those are explainable by hallucinations. I can't tell you all with any certainty. Oh, also, it's so easy to trick the brain. It's super easy to do it with psychedelic drugs or any hallucinogen, right? You can cause somebody to see something that's not there or alter somebody's visual perception. However, you can even do it in the lab. You can induce the sensation of you standing behind your own body looking at yourself. You can induce that, not using any drugs. So, the brain is very fallible. It is not perfect, and it's easy to trick. And so, yes, definitely, at least some of those cases are hallucinations, at least. Any new research on Alzheimer's for a cure? Yes. There's Alzheimer's research is one of the areas of greatest activity in neuroscience. The answer, will there be a cure tomorrow? I'm unaware of any very compelling avenues of research. A recent avenue. Don't Stop Believing. Yeah, hey, how's it going? That avenue was. Actually, yes. Oh my gosh, I almost forgot about this. There is some really interesting preclinical evidence for Alzheimer's disease specifically. So it turns out. Well, let me finish what I was saying before. So, Alzheimer's disease, what is it? We believe, very confidently believe, that it arises from the accumulation of two things, amyloid beta plaques and neurofibrillary tangles. Amyloid beta plaques on the outsides of neurons, gunking up the outside, neurofibrillary tangles on the inside of neurons, gunking up the insides. Over time, it's sort of like if you have like a piece of lint in your pocket, right? And it's there for days and weeks and days and weeks, and it sort of grows. It's sort of a similar kind of process where like more fibers are sort of aggregating on that little lint ball. And that's, you can think of it sort of similarly when it comes to amyloid beta plaques, neurofibrillary tangles. Well, one of the recent approaches to trying to cure Alzheimer's disease was, hey, you have these two accumulations, why don't we just get rid of them? And some really brilliant, creative scientists found a way to exploit the immune system to clear out those plaques, essentially by using almost like a vaccine. And they were able to show reduced amyloid beta plaque densities. However, there weren't significant improvements, and people did have sort of immune system reactions. So that was frankly, it was surprising when it failed the first time. But there was a recent trial by Eli Lilly that I don't think anybody was particularly surprised it failed because it had been tried before. Anyways, so, okay, back to the drawing board. Well, just like the search for treatments for COVID-19, one really useful thing would be if there's a drug that's already out there, already been used, already been deemed as safe by the FDA and equivalent departments in other countries, and it just happened to be therapeutic in Alzheimer's disease. Well, I think it's salbutamine or salbuterol, an asthma medication, essentially something that would be in an inhaler, was shown in vitro, I believe it was in vitro, to prevent amyloid beta accumulation. I think also maybe in preclinical models, in animal models. I'm not 100% sure. But that would be very, very interesting. The reason that they even tried this was it turned out that epinephrine, adrenaline, you might be more familiar. We call it epinephrine in the brain, adrenaline in the body, for no good reason. It turned out epinephrine can have this effect, but epinephrine doesn't really diffuse into the central nervous system, but this other drug does. And so, hey, if this works, this could be just, it wouldn't be a cure, but it would be one of those things that renders other treatments more effective and just extends somebody's quality of life higher, elevates their quality of life for a longer period of time as they're developing Alzheimer's disease. Fahad, quick question to link it to my research. Oh, what is the connection between neuroscience and happiness? Oh man, wow. That is literally a multi-billion-dollar question, multi-trillion maybe. Oh, just read salbutamol. Yeah, asthma med reduces neurofibrillary tau tangles. Yeah, exactly. Yeah, I didn't remember it because it's not a very specific treatment. It's like, but hey, if it helps, Gordon Hoyt, right? Why not use it? So happiness is extraordinarily difficult to define from the perspective of a neuroscientist. Different people associate happiness with different things. The way I think about it is we didn't evolve to be consistently happy. And there's a difference between like happiness, in my mind, this is like almost pure philosophical, like postulating at this point, but as a neuroscientist, this is how I think about it. We didn't evolve to be happy all the time. We evolved to experience moments of happiness and then come back down to some sort of stable, contentedness. I do think we have the ability to achieve contentedness, satisfaction, which is not the same as happiness. I think it's important to be happy, but and this partly explains why it is that people who live lives that you see as being incredibly privileged and wonderful and with wonderful resources, how they can still complain about stuff, right? That you would probably would think like, I could never be unhappy for a moment if I were in his or her shoes. Well, that's because the brain adapts. The brain reaches homeostasis, and we just did not evolve to have this elevated level of happiness consistently. But contentedness is different, and that is part of the reason. I'll give you one little neuroscience mechanism is because of the way the mesolimbic dopaminergic system operates. So dopamine neurons in the ventral tegmental area send dopamine to another part of the brain through the limbic system, let's just call it. It's called the nucleus accumbens, or the ventral striatum, and that signal is very, very important for your expectation that something good is going to happen, which is what I think a lot of people think of as reward. It's not quite the same, but it's similar. It's also the signal that people experience when they do pretty much any addictive drug: heroin, nicotine, alcohol, cannabis, and those neurons. The way those neurons evolved is that they exhibit the way they tell the other part of the brain, "Hey, this is a moment of excitation." That's a nice little neuroscience pun. Is through transitioning from tonic firing to burst firing, meaning that they're just sort of like firing like this, and then all of a sudden it's brr, brr, brr. Oh, like that like if you are placing a bet at a roulette wheel or something like that, and you ostensibly think you're going to win, that signal is elevated, that excitation, that moment of excitement. And so, but the problem is that those neurons, not only did they not evolve to be able to do this, but they are incapable of just constantly going brrr, right? Eventually they'll literally die if they do that. And so it is neurobiologically impossible to sustain that level of excitation for a lifetime. So yeah, okay. I think we are getting a call. Let's see if this works. Oh, nice. So Chris, it sounds like we are connected. How are things in San Francisco?
Things are absolutely fabulous. Happy 5th of July.
Likewise.
I think it'd be more impressive, rather than blow up $500 worth of fireworks, burning $100 bills. I think that would be more impressive.
That would be fun. I'm sure people would get kind of angry, but yeah.
Yeah. Anyway, I have a question for you. I studied some of the history of the Civil War, and part of the study was about a place called Andersonville. It was a prisoner of war camp where Union soldiers were housed by the Confederacy, basically in an open field in Georgia. And I got a book written by a doctor who was sent there as a Union soldier, captured Union soldier. He documented his stay in Andersonville, and he noticed this: the soldiers that were more physically robust and strong in stature seemed to die quicker and sooner for no apparent reason than the soldiers who were scrappier, smaller in stature. He postulated that this is perhaps due to soldiers who were bigger, the bigger gentlemen, the larger gentlemen, were used to having it their way in life, having things more abundantly, food and whatever, where the scrappy soldiers, the smaller men of stature, were used to getting by and making do. The name of the book was called Andersonville. It was written by the gentleman who was actually there, so I have a first edition copy.
Awesome.
My question is, how much of mental force can be attributed to good health. In other words, can you bring to bear, for example, I went to the hospital once for pneumonia, and the doctor said, you got pneumonia, and I said, no, and immediately my mind sunk, my heart sank, my emotions sank, but then I stopped myself, and I said, it's not going to beat me. And I just really forced my brain all day and all night for 7 days in the hospital to fight back against the pneumonia. And I said, this is not going to beat me. And I feel like it helped. It attributed to a recovery. So my question is, how strong is the power of the mind to help your health overall? Thank you. I'll hang up and hear the answer.
Super interesting topic. Thanks for calling, Chris. Good to talk to you. So, that's an interesting phenomenon. Another, just like solely before we get into the relationship, the mind-body sort of relationship, there's also the reality that like people who are larger, who are perhaps more muscular, they do have higher caloric demands. And while, the body will begin metabolizing, muscles and turning them into amino acids and then breaking those down into carbohydrates, or some carbohydrates, that caloric demand, it doesn't adapt perfectly. And so I could imagine, various maladies emerge from just a consistent severe caloric deficit. And it's just more likely to happen given, I'm sure they were all given the same amount of food, some kind of ration, or if they even got food, given that it was a, POW camp. And so, smaller people were literally able to exploit that number of calories to make them last longer biologically, whereas the larger guys, they were just inevitably going to be at a caloric deficit for so long that, various cardiovascular anomalies could occur, or kidney failure. I'm sure they were drinking a lot, these types of things. But anyways, the point is well taken. It sort of reminds me of A Man's Search for Meaning, the book by Viktor Frankl, who was a former, a Holocaust survivor, and also a psychologist. And, his description, I don't know if, it's a very short book. I think everybody should read it. It's a very short, very, jaw-dropping book to read. Just, of course you learn about the Holocaust and everything, but just hearing it from his perspective is just nuts. And he also, identifies, the people who made it, who weren't just executed, were those that could derive some kind of meaning in their life, despite being in a horribly, evil, banal kind of environment. Anyways, so, and then I hope you didn't have COVID-19. You said that you had pneumonia, but if it was only 7 days, then I suppose it was unlikely. But yeah, I'm glad to see you came out the other end, regardless of what caused it. But for sure, there are measurable effects of things like optimism or the belief that some treatment is going to work on the efficacy of those treatments. Unfortunately, I've never seen a study that actually, parses down or gets to the granular details of what it is specifically, what mechanism it is that, improved mood, let's just say, just generally improved mood, what the ramifications are for the relevant biological systems in, not COVID, okay, that's good, relevant systems in whatever they're suffering, some lung respiratory related, pathogen or malady or whatever, or if it's cancer, or if it's, whatever, any kind of disease. But there have been detectable effects. And we could speculate here, right? A lot of these maladies have some relationship with the immune system. The immune system is a magnificent, really amazing system, but it is sensitive to it is sensitive to the guidance from the brain regarding what the most imminent threat to survival is in this moment. And so, the immune system, when it's active, it's very distracting, right? It makes you, your nose run. It makes your throat itchy and cough a lot. But so the immune system is all of those are a byproduct of the immune system fighting off this pathogen. But if all of a sudden there's a lion in front of you that's going to attack, then you have this extraordinary fight or flight reaction. It's a source of stress, and your hypothalamus, a bunch of your HPA axis kicks into gear, hypothalamus, pituitary, adrenal axis, And essentially, among all the various molecules that it releases, glucocorticoids, or cortisol you've probably heard of, will suppress all of that immune system activity. Because it's like, it doesn't matter if we're going to die from pneumonia in a week, this lion's about to kill us. So we'll deal with the pathogen later, and it's significantly immunosuppressive. And so if somebody's suffering from depression, if somebody's pessimistic, if somebody's highly anxious, chronically, that immunosuppression is a real thing. Like it's a measurable thing, and so that might yield deleterious health consequences. But that's almost speculation, almost pure speculation. But I would imagine that it's related. Because, the difficulty is that, like, okay, let's take pneumonia. That's a great example, actually, because theoretically there was some kind of bacterium or virus that has infected your respiratory system and caused you to have pneumonia. There's no known system by which, like, the limbic system in the brain, which is the part of the brain that is most concerned with regulating mood. Like, if you felt optimistic, it's because it was happening in the limbic system. There's no, like, connectivity between the limbic system and the like respiratory epithelium, like the cells that compose your respiratory system. Hey, Leonora, good to see you. Hope things are going well on your side of the planet. So yeah. So the short answer is yes, there's definitely a connection, but we don't really know what those mechanisms are. But it might be the relationship between chronic stress-associated signaling that's associated with depression, anxiety, pessimism more broadly, and the immune system. That's just one potential mechanism. One more thing. So also, chronic stress will also influence metabolism. And so, your ability to derive nutrients from the food that you're eating is subject to being influenced by how stressed you are, how content you are, or how, depressed or anxious. So that's another potential mechanism. All right. Thanks for calling, man. It was good to talk to you. All right. Great book. He states that we may not have the power to change life circumstances. Live now. However, we can change how we think about them. Exactly. Right. I believe you're referring to A Man's Search for Meaning. Yeah, it's a short book. I mean, you can read it in like a day. It's worth it. Okay, what's in it? Oh, okay. So yeah, Chris said the name of the book was Andersontown, I believe. I help an ICU RN that works with COVID patients and scopes about COVID. Oh, that's awesome. Well, it's not awesome that your friend, your nurse friend, has to deal with COVID. That's awful. But it's great that they're talking about it. Anxiety is the worst, especially right now. Yeah. They need more calories, indeed. Right. It's better to boost your immune system right now with COVID because of those cluster storm things that get overreacted. So Lauren Cantu, what you're referring to is cytokine storm, I believe. And so there's really nothing you can do about that. So the reason being, okay, so probably many more of us have heard about the epidemic of the flu epidemic of like 1918-ish, right? The Spanish flu epidemic, than we ever would have before. When I moved to Philadelphia, I happened to learn about it a lot because Philadelphia was like the epicenter of that breakout, and hundreds of thousands of people died, and there was even a parade down Broad Street, which you can't see it from here, of like tons of people, hundreds of people, thousands of people, all commemorating this event, this tragedy in the city, and it's wild. Like I think a year later we had COVID-19. So weird. Anyways, one of the theories as to why it was that younger people tended to be the ones that died most frequently from the Spanish flu was that there's a bunch of really interesting explanations. I actually don't think that this is the correct one, but one of the explanations was that, generally speaking, the immune system activity of somebody in their mid-20s is far greater than that of as we get older. And so as a result, this particular influenza strain might have been such that people with healthier immune systems were actually more vulnerable because they had that cytokine storm where the immune system is essentially just carpet bombing your body, right? It doesn't have any antibodies specifically targeted to COVID-19 or the influenza virus, but what it can do is just kill every cell that virus has come in contact with or will come in contact with, and that is, that's why people can begin to have kidney failure, severe pneumonia, have to get, intubated and put on a ventilator, and so on, right? Strokes. Actually not, strokes doesn't really fall into that category, but but I think, we don't know enough yet about COVID-19, the biology of COVID-19, to know for sure. And in fact, I think there are better explanations of why that happened in 1918. But no, I mean, if I had to choose, having a robust immune system would be what I would want. But the priority should be to not catch it in the first place. Not only for your own health, because it's becoming clearer and clearer that there seem to be lifelong consequences of being infected with COVID-19 that are not like you get over it and then you're finished. Like your respiratory system may be affected for years, many years, or maybe forever, despite the fact that you healed. And then there are potentially, neurobiological consequences of COVID-19. So you just should not. Your goal should be to avoid it altogether, not only for your own health, but for the health of the people you love, and just other people, people you don't even love, you never even met. Okay. I was in hospital for a week with sepsis. Had no clue. Whoa. Being a primary immune deficient person, can you explain how I don't get fevers? It's perplexing. Yes. So a fever, like most of what you think of the symptoms of being sick, most of those are not generated by the virus or the pathogen itself. It's not like the virus is causing mast cells to secrete a bunch of histamine, right? It's that the immune system has evolved such that all of these responses are a way to attack this pathogen, right? To get rid of the pathogen. That's why you produce all this mucus and it comes out of your nose, to just flush it out so it doesn't, spread within, your whole respiratory system. And a fever is also a byproduct of that immune system reaction. The virus or the bacteria is not like turning up the dial on the thermostat of your body, but rather it's your immune system reaction kicking in a high gear. And actually, fevers themselves, this is a misunderstanding that I certainly had, but I think is extremely wide. Fevers themselves are not particularly dangerous. Like, they're just a sort of an indication of what's going on in an immune system level. Of course, super high fevers are, but fevers in and of themselves are not. You don't need to the priority shouldn't be to lower the fever. The priority should be to treat the illness. Oops. Your bub is 8 weeks old. Did you have a baby? Your baby is 8 weeks old. Oh my gosh, Tiger Beast, congratulations. My baby is about bit over a year and a half now. That is, so congratulations. What do babies dream about? Well, it's tough to know for sure because no matter how many times I asked my daughter what she was dreaming about, she wouldn't tell me. But we probably could speculate pretty accurately. So first of all, babies that young aren't really, their whole conscious experience is completely and utterly different from yours and mine. They're not really forming meaningful memories. In fact, wait, you said 8 weeks old? 8 weeks. Yeah, it's probably still like sensory information is still like kind of, they're still trying to figure out what all this sensory information means. Like, visual systems, like, for sure, your baby's vision is not even remotely as close to as good as yours. They probably can't see very far in front of them. And so, the whole point being that, like, they're not experiencing the world in a coherent way, really. Bye. Okay, does fear affect the stamina? Sure, we can talk about that if you like. But they're clearly things are happening while they're asleep, right? You'll totally see it. It's so cute. But they'll just do like little twitches and like they'll smile sometimes. And probably what's happening is the same thing that happens when we have dreams, which is just spontaneous activity in the brain necessary for connections to form between different parts of the brain, different neurons in the brain. And because it's the same machine that governs our ability to exist in the world, they react accordingly. And so, this neuron needs to connect with this neuron. These are the neurons that control the movement of the lip. And for this connection to form, there needs to be activity between them. And so as a result, there is activity between them, and then they get this little jerk. So it's probably not like a coherent dream like you and I might have, but there is something going on there. And it's almost certainly necessary for the development of their brain, unless, like their subconscious trying to teach them a lesson, right? All right, I should probably call it a day there. Thanks for hanging out, everybody. I really appreciate it. Hope you all had a lovely weekend. I have a YouTube channel, youtube.com/anthropoid. What I do there is I go into a specific topic for the first 20 minutes or so before I start this live stream. You can check it out, youtube.com/anthropoid. You can search Anthropoid Ian. I have a podcast. It's called Wired to be Weird. We talk about things like dreaming, dementia, drugs, and those are just the D's. We talk about a lot of stuff. Wired to be Weird, iTunes and Stitcher. And I have a Patreon. I know things are tough at the moment. If you have the capability, I would appreciate any kind of support. Patreon.com/anthropoid. All right, everybody, have a great weekend. I'll see you next time. Same time, same place. See you there. All right, YouTube. Thank you all for watching. I hope I didn't miss a bunch of comments. Of course I did. I'm so dumb. Anyways, thanks so much for watching, everybody. I appreciate it. I'll do a better job next time of not missing comments. And I hope all of you, if you have any tips as to what I should do better on this channel, I am all ears. Otherwise, have a great weekend. Stay safe, stay sane. I'll see you next time.